Unit 7.7. So we're going to get into taking some of these theories that we've been accumulating here with equilibrium constant, and now start doing some calculations with those. So let's jump in. So most of these, again, we've already learned all the theory. We just now have to adapt some math to it. So let's break some things down here. So what do we got? We have moles of the reactants in a 1 liter container. So I don't think you have to really write these down, but I'll write them down anyhow. I don't think I'll be doing this the entirety of the lesson, but moles divided by liters will give you molarity. So, and just to save space, I'm not going to write the sig figs until I'm ready to report an answer. But those 0.5 in 1 liter container, that's 0.5 molar. Okay. Let's go and rewrite the equation again. Actually, you know what? Let's do it. Let me move this a little bit higher here so we have additional room. Okay, so we had H2 plus I2 going to 2HI. Initial change equilibrium. And I'd already recorded or calculated, I guess, that we started off with 0.5 molar. Now, again, sig figs and units, I just don't have enough room in this table to put all those things, but we're definitely going to keep an idea about that as we move forward. Okay, and we're already given a Kc. Refresh our memories. The expression is the concentration of products raised to their coefficients, and the reactants, whoops, I2, let me clean that up a little bit. Okay, and their coefficients of 1 raised to the power 2. So there's our equilibrium expression, and it says for us to calculate the concentrations of all species at equilibrium. So this is not a completion reaction, so you're not going to lose all of your reactants, all your limited reactants. So this makes it a little more difficult to obtain an answer. But what we do know is that the ratio between the items have to go with the coefficients, the 1 to 1 to 2 ratio. So we're going to lose some H2. How much? X. We're going to lose some I2. How much? X. And we're going to gain some HI. How much? 2x, twice as much. So we have a equilibrium amount of those 3 values. Now we can plug those into our equilibrium expression and we can solve for x. And once we've solved for x, we can put them back into the 0.5 minus x or the 2x or whatever we need to formulate our equilibrium concentrations. So the Kc was given, that's 54.3. We were given that the equilibrium amount of HI is 2x. I'm going to kind of go back and forth here between colors. So 2x, and don't forget that is squared, because our equilibrium expression says it has to be squared. And then on the bottom, we have 0.5 minus x times 0.5 minus x. I'm going to shorten that and just do this, and I think it might become evident why I'm doing that. So again, 0.5 minus x is just, 0.5 minus x times 0.5 minus x is what I have here, 0.5 minus x squared. So to get our calculation going further, if we take the square root of everything, the square root of 54.3, the square root of 2x squared, and the square root of 0.5 minus x squared, We get that. So now we can multiply both sides by 0.5 minus x, and that would give us, of course, we'd have to do the square root of 54.3. I think that's actually, I'll break this down a little bit further. I'm not going to break these all down like this, but I'll do this one for you here. Now, on my calculator, I left more digits than 7.37, but that's all I wrote down here for sake of room. And then I'm going to multiply both sides by 0.5 minus x, and that's going to give me 3.685 minus 7.37 x equals 2x. Get the x's on the same side of the equation, and we would have 9.37x equals 3.685. X equals somewhere in the ballpark of 0.393 molar. Is that our answer? No, it's not our answer, but it's very close. Our answer, we need to plug those values back into the x component here. And so 0.5 minus 0.393 is 0.107 molar. So that's for H2, and it's also for I2. And then all we need to do is just multiply 0.393 times 2 to get the HI value, and that's going to give us 0.786 molar for, again, the HI at equilibrium. So I'd like to have you guys get in the habit of boxing those answers if you have lots of work laying around here, so we can easily, the AP readers can easily figure out what you want to be graded as the correct answer. But all that work is still going to be important to validate your answer. If you write down answers without all that work, it's as if you didn't write any answers down. Okay. Now this is a multiple choice question, so remember that these AP multiple choice questions are designed to be done without a calculator. Well, they're certainly easy to be done when the answer's already told you. So let's figure out how we got to 0.05 there. Let me rewrite the equation so I have a little more room. These ICE tables are not mandatory, but highly suggested because it's very easy to visualize what's going on. So when you read the question, the pressure in the flask was initially at 1 atmosphere. Well, it also mentioned that was the only item that was in the flask. So that means initially that is our starting material. I'll write 1 atmosphere there, but I probably won't write the units for the rest of these pieces here. We have 0, we have 0. We're going to have to lose some of that. We're going to have to gain. We're going to have to gain. And then we'll have some equilibrium, in this case not concentrations, we'll have partial pressures. KP, by the way, whoops, we're going to solve for KP. Okay. What else do we know? We know at equilibrium, if you add up all those gases, it equals 1.2 atmospheres. I don't have enough room to put that little m there. Let me try to, I'll do it that way. Okay, so when we add up all those partial pressures, it has to equal 1.2 atmospheres. So again, we don't know these changes, but we know it's a 1-to-1-to-1 ratio between all of the items in the chemical reaction, so we can give them the same variables. So 1 minus x, 0 plus x, and 0 plus x. I don't know if you can figure this out yet, but we will now know the equilibrium concentrations. And by the way, why do we need the equilibrium concentrations? So we can plug them into our Kp expression. If I am completing this multiple choice question, I probably wouldn't write all of these things out, and you certainly don't have to on a multiple choice question. If it was a free response, you would though. So let's go back to our equilibrium. 1 minus x, partial pressure of CoCl2 at equilibrium, plus our partial pressure of CO at equilibrium, plus our partial pressure of Cl2 at equilibrium has to equal 1.2. So before we get too much further, there might be a couple things we can kind of cancel. A minus x and a plus x we can cancel. So what is x going to equal in this case? I think just take the 1 and subtract 1 from both sides, and you'd get 0.2 atmospheres. So we can take that value, and let me erase these now so I can show you. And we can stick them in those spots. So the products have a value of, we'll go back, we'll leave this as blue. So we have a 0.2 for the CO, partial pressure. We have a 0.2 for the Cl2. And then down below we have 1 minus 0.2, which is 0.8. Now that would look to you like, how am I going to do this without a calculator? Can be done. Can be done. What's 2 times 2? 4. Yes, we have the decimal places. Don't worry about the decimal places. Let's worry about often, not always, but often we can just literally worry about the numbers, and all we need is to get to one of those 4 answers. And then on the bottom we still have this 8. And yes, we got the decimal places. No worries. But 4 divided by 8 is a half. Which of these numbers reflect a half? Right there. That's a trick that I would suggest. If you have your own trick, if you don't want to use any tricks and use full math, that's fine. You just won't get to use a calculator on the AP exam for these questions. Okay, so like all these other ones, the multiple choice, I've already given you the answer. So let's figure it out. So the answer is already 36. So we have an equilibrium equation, so that means we have an equilibrium expression we can kind of think about. So that would be z to the power of 2, and I should use brackets. Brackets. Okay, so there's our K expression. What else do we got? Like I said, the IC tables are often really nice to use. What do we know? We know 4 moles of X and Y in a 1 liter container, so that's 4 molar. And what else do we know? That when it's all said and done, we make 6 of the Z's. So if you start off with 0 Z's, you'd have to add 6 of them. If you know this is a 6, then you know, because it's a 1 to 1 to 2 ratio, you know that this 6 has to be half of these numbers for the other changes. 4 minus 3 is 1, 4 minus 3 is 1. Now I think this is going to become a little bit easier. I think we can all do this pretty easily without a calculator. 6 to the power of 2 divided by 1, and another divided by 1. So I think that's how we get to that 36 answer. Okay, answer B. We already got it. Let's figure out why. Okay, we have our equilibrium reaction. 2 moles of H2, I2, and HI. They're all in the container initially at a 1 liter. So let's look at this again. We have not run across this yet. We have been programmed that the changes on the reactant side we're going to lose negatives. We're going to put negatives there, and the HI we're going to put positives. This one's a little more difficult to do, although usually the case, because that K value is large, greater than 1, it's going to proceed more left to right. But I'm going to show you something that we'll spend a little bit more time discussing here in the next unit, but I think it's a good time to introduce it. Although we have actually introduced the reaction quotient Q, but we haven't been able to do anything with calculations for Q, and we haven't done any interpretations of what Q actually will represent for us. But Q will be a tool for us. Calculating Q will be a tool for us to determine, are we going to have a subtraction on the reactant side and a product and an addition on the product side, or is it actually proceeding from right to left, meaning that you'll have this occur. And unfortunately, it can happen in both circumstances. So the way that we will be able to identify that, if we're not in the lab and we can't visually see it occur, is to calculate this Q. And Q, you use all of the same ideas, except that when we did K calculations, we used that equilibrium row. But today, for Q, we are going to use the initial amounts. That's the only difference. So we have our equilibrium expression, the HI up top to the power of 2, and then the reactants on the bottom, they're both powers of 1. So I think that's pretty easy to calculate that as 1. Now, compare it to K. Kc is 50 in the question. So K is much greater than Q. And again, we haven't defined this. This is the first you've seen this here. But if K is bigger than Q, the reaction proceeds, meaning that we know that these are going to be negatives and this is going to be a positive. We had a clue that that was going to be the case, but we didn't know that for certain until we compared the Q and the K values. If you have a reaction where, not a reaction, but if you have a calculation where you're comparing Q and K, and you have this situation occur, then the reaction proceeds this way, and instead of what we just wrote down correctly, it would be this in that case. And it can happen. It can definitely happen. But that's not what we have today with this one. And so I'm going to proceed as I was going to anyhow. Okay. I don't think that we can go any further with that ICE table, and we will not have to go further in that ICE table to answer this question. What is the question? Which of the following will occur as the system moves towards equilibrium? So it really wants to know what's going on with the change, and we just identified that the reactants will lose and the products will gain. So which of those answers match up with that? HI is a product, so more HI will form. And that's not the first time we're going to, I'm sorry, not the last time we're going to be able to see this Q versus K relationship. We're going to have a lot of opportunities to practice that. Okay. Let me see what else we got over there. Okay. Problem 5 of 6. Let's see what we got going on here. Another multiple choice question. Did we have an answer? Oh, we had an answer like these other ones. Answer B. So let's figure out why we like answer B. So I have room here below the equation So I'm not going to rewrite the equation. I'm just going to put my ICE table there. K is given. And it says, what's the equilibrium concentration of BCl? That's the product. If the initial concentrations of Br2 and Cl2 contained in the flask at 400 K are 0.3 molar. So let's put in a 0.3 for Br2 and a 0.3 for that, and we have a 0. Now, if we have a 0, we didn't have a initial amount of an item, then we don't need to look at the Q versus K. We know you can't subtract from 0, so that means you'd have to add from 0. So we already know which way it's going to proceed to get to a dynamic equilibrium. We have the 1 to 1 to 2 ratio this time. So x, 2x. So we have 0.3 minus x, 0.3 minus x, 0 plus 2x is 2x. So our equilibrium expression, K is equal to 7. And we take our products, 2x, and then coefficient of 2, so we raise that to the power of 2. And then on the bottom we have 0.3 minus x times 0.3 minus x, which is really 0.3 minus x squared. And I think we've had a question similar to this before. Take the square root of everything and rearrange to get x by itself. And when you do that, you'll get that. Okay. What do we got going here? By the way, if you don't like doing square root of 7 with a multiple choice question, you could make this into a number that would be handy for you. What could you take the square root? I bet you could take the square root of 9. Many of you don't like to do that because that's not the actual correct answer. But remember that on these multiple choice questions, now this is from many years ago, this particular question, and they've slackened a little bit. They've taken a little bit off of the calculator portion of these multiple choice questions, so they probably wouldn't ask this question at this point. But if you're presented with that, I think a lot of people would be hard pressed to try to take the square root of 7, do that in their head. But you could do the square root of 9, and that would get you a nice approximation and likely nail you down to an answer here. So I don't see 0.17 up there in any of these answers. Why? Because this isn't our answer. It wants to know what's the concentration of BrCl at equilibrium, which is 2x. So you need to multiply that by 2, and that's how you get the B. Okay, so this one appears to be a free response question. I think this might be, yeah, we have a couple smaller, shorter questions after that. Expression. So I had told you that often we will start off with these free response questions. Not always, but start off with these as a write the expression. Okay. Very generous. They're going to give you 2 points if you can write that expression. Next question. You got 1 mole of each gas. So that means all 3 gases are in there. And it's a 2-liter container. So remember, molarity is moles per liter. So it asks for initial molarities. 1.0 moles divided by 2.0 liters. I think most of you should be able to get that there. So all the gases have that molarity to begin with. To reach equilibrium, would the HF increase, decrease, or remain the same? Whenever you see questions about that, this is our second, I guess we'll call it still an introduction, Q versus K. K was given 320. I would consider that a large K. Q is not given, but remember the initial molarities are given. So Q and K, same exact setup for mathematics, just that K uses equilibrium numbers and Q uses initial numbers. So it says support with a calculation. We're gonna support it with a Q calculation. So we're gonna just look at our expression in part A. Yes, it says K equals, but we're gonna do Q equals. Still the products, 0.5 squared on the bottom, 0.5 and 0.5. I think that's gonna be easy to calculate that. Let's go with the sig figs too. So Q is 1. Q would be much smaller than K, or you could say K is much bigger than Q, whatever you want, because 320 is our K value. So that means that it proceeds, the reaction proceeds from reactant to product. So you would be able to make more product. Is HF a product? It is a product. So increase. And then that is our supporting calculation. What else we got? Equilibrium concentrations. So how are we going to tackle this one? I don't have a lot of room here, so I left myself another page that I could put this work. If you need to refer back, we can go back, but the equilibrium constant was 320. Our ICE table, I don't think I did an ICE table. I did not. So maybe we'll put an ICE table over here. H2, is it H2 plus F2? It is. And we had 0.5, we had 0.5, and we had 0.5. Minus x plus 2x. And that's going to give us 0.5 minus x, 0.5 minus x, and 0.5 plus 2x. So we've been presented with this almost identical same kind of setup a number of times here now. And so 0.5 minus x on the bottom times 0.5 minus x is 0.5 minus x squared. Take the square root of everything, rearrange your x's. To save us a little bit of time, I'm going to go to my answer for x, but I broke that first one down where we had to do that. Take the square root of 320, take the square root of 0.5 plus 2x, take the square root of 0.5 minus x. By the way, both those were to the powers of 2. So is x our answer? No, it wanted to know the equilibrium concentration of HF. Sometimes it'll ask all the equilibrium concentrations, but this time it only wants to know what that value is. So it's 0.5, so HF concentration equals 0.5 plus that. Okay, so you'd calculate that out. We have a couple more quick questions here. The AP folks are starting to introduce these particle diagrams. And particle diagrams should not be any harder than our mathematics that we've been doing previously. It's just that you have to look at the particles instead of having set molarities or pressures, so forth. So this question says we have some red spheres. Let's give it. Red spheres are A, Blue spheres are B. And then if you have a cluster, that's the products AB. So it says rank the reactions in order of decreasing equilibrium constant. So remember that if the equilibrium constant is huge, it moves more left to right, meaning that you're going to have lots of AB when you're done. If the equilibrium constant is very, very small, you're going to have very little of that way and a lots of this way, meaning you'd have at the end of the day lots of A plus B laying around. So all you got to do with this question is count up. I guess you could count up everything, but to make this go a little bit faster, I counted up the number of ABs. So in this one, I counted 9 ABs, I counted 3 ABs, those are the clusters, 7 ABs, 1 AB, and 5 ABs. And I probably wouldn't, if I was taking a test right now, have written those out. I would have kind of kept those ideas in my head. But if I'm going to rank these, this has the largest equilibrium constant because that produced the most products. Then our next would be that one, and then this one, and then this one, and this one only makes one product, so it would have to have the smallest equilibrium expression. And our last question, I already have the work to go with the answer on this one, actually. Okay, so we have a little particle diagram here. What do we have? We have white. We'll call those white balls. We have dark balls. We'll call those black. And it makes a combination of a white-black. Okay. We don't really know anything about initial change, but we do know about equilibrium because this is the equilibrium amounts. It says that that container is a 2-liter container, and each one of these particles is a 0.4 moles. So what do we actually have in here? The white, we have 2 of those. Okay, so it's 2 times 0.4 moles divided by 2 liters. Where do I have that? Well, I guess we could say we have that, right? No, not right there. It'll be this one, sorry. Okay, and then black. I have 4 times 0.4 divided by our 2 liters. And so 4 times 0.4 is 1.6, so that is that one. So this is for the white, this is for the black. And then remember that the WB has to go on the top of the fraction there. And we have 2 of those. I'll just write it here. So 2 times 0.4 divided by 2 liters. And that is that one. So crank out that math, and answer is 0.125. Actually, looking at 2 sig figs and 2 sig figs, I think I would, if this was the test question I put together, I probably would have changed this because that 5 doesn't have anything back there, and I don't know if everyone learned uniformly how to round that, but I think most people learned not to round that 5 unless there were other digits behind it. So probably, I guess what I'm saying is on the test, I would be fine with that answer, and I'd be fine with this answer. This one is more technically sig fig correct for this course, but either of those would be okay.